In the last video, we introduced the idea of the root locus method, which is a way of describing how the closed loop poles change as we change a parameter. And that although this is a general method, oftentimes we'll talk about it in the context of the parameter being the control loop gain, K. And so in this video, we're going to talk about the 5 rules you'll need in order to essentially create a basic sketch of what that root locus looks like. So this first rule talks about the number of what we're going to call branches of the root locus and a little bit about the location of these. And so there's going to be as many branches as there are open loop poles, or actually as closed loop poles. And what we're going to show is that those start at the poles of L of S, the poles of the open loop transfer function. And that's when k is equal to 0, and that as k gets very, very large, goes off to infinity, these are either going to go to the zeros of L of S, or in rule 3, we're going to see that these converge towards asymptotes. And so how do we show this? Remember that the characteristic equation, one way to write this is the fact that L of S needs to be minus 1 over k. And so if another way of rewriting that are these two expressions. This one when we're going to use k going to 0, and this one when we're using k go off to infinity. So remember, we're going to write that loop transfer function L of S in terms of its numerator n of s and its denominator d of s. And let's say that the order of the numerator is m and the order of the denominator is n. And so this may get a little confusing, or we're using n twice, but we're using it very different ways, so it should be pretty clear. So if we rewrite our characteristic equation in terms of n of s, d of s, and k, then we get this expression. And so if k goes to 0, then that means that the criterion for s being part of the root locus and satisfying this expression for the loop transfer function just means that the denominator has to be 0. So essentially it's the roots of the denominator of L of s. And so that is actually the poles of L of s. And so since it's an nth order polynomial, then there are going to be n of these poles, which means that there are going to be n branches. And those start, because we're talking about k is equal to 0, those start at the poles of L of s. Now as k goes off to infinity, we're going to use a different expression for the characteristic equation, and that's given here, where we just move k over to the other side by dividing the whole thing by k. And that means as k goes off to infinity, this term goes to 0, and we're left just with n of s is equal to 0. And so the s values that satisfy the root locus are the ones that are the roots of the numerator of L of s. And those are the zeros of L of s. So again, this is the zeros of the loop transfer function. Remember, L of s is g of s, d of s, where d is part of the controller, the part of the controller that doesn't include the parameter k, and then perhaps any feedback transfer function h of s. And so we said that this is an mth order polynomial, which means that there are m of these zeros. And so out of the n branches, because n is going to be always greater than m, out of the n branches, m of these converge to the zeros of L of s. So that means as k goes off to infinity, some of these branches, and in particular m of these, converge to the zeros of L of s. So let's see this as a quick example. We're going to take a look at this example several times for all the different rules that we're going to consider. So if we look at this loop transfer function L of s, so this again is the combination of g, d, and h, that there are no zeros in this case. So m is 0, and there are 3 poles, and the poles are at 0 and -4 plus or minus 4i. So we have 2 complex poles and 1 real pole at 0. And so n, the number of branches, is going to be 3. So there's going to be 3 branches for this root locus, and they're going to start at these poles, 0 and -4 plus or minus 4i. And so these are the x's that I'm indicating here, 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 and here. And so this is where the root locus branches are going to start. And because there are no zeros, these poles will all tend towards asymptotes, which is the third rule that we'll go over. The second rule is a really handy one, and it just says that the root locus, the values of S that satisfy the root locus criterion, are always on the real axis to the left of an odd number of poles or zeros. And so this is a very nice and very easy one to implement. And this really comes from this notion of the 180 degree phase rule. And so poles and zeros, they're either going to be real, in which case they're going to end up on the real axis, or they're going to be complex valued, and they're going to come as a pair of complex conjugates. And so if our test point, remember we're going to test a point S naught, if this value, we're essentially determining what the angles are of all of these elements, these poles or these zeros, from their horizontal to that test point. And so we want all of those to sum up to be equal to 180 modulo some amount of 360. So if a zero or a pole, so this element right here could be a zero or a pole, you see that the angle that it needs to point to the left of it is exactly 180 degrees. So this is 180 degrees, and so that means that any real valued pole or zero automatically adds 180 to a test point that is to the left of it on the real axis. If we look at a set of complex valued poles or zeros, which is this case over here, then we notice that even though this angle phi1 may be some arbitrary number depending on where the test point is and where this pole is, if we look at the angle that this phi2 that the complex conjugate adds in, you see that these are complementary angles. And so they always sum up to be 2 pi. And so this means that complex conjugates will never add an element of 180. This is essentially 2 times 180, or 360. And so this is not going to be a point that satisfies the root locus, because once they sum together, they're not going to be 180. And so again, we're talking about an odd number of poles or zeros. If there was another pole or zero sitting over here, then there would be 2 factors of 180, and then this test point would not be on the real axis. And it wouldn't be on this test point, which is on the real axis, would not be on the root locus. So again, I said this is going to be easy to implement, so let's see this as an example. So coming back to our example that we saw before, we have these 3 poles. And so what the rule 2 says is that any point on the real axis that is to the left of an odd number of poles or zeros is on the root locus. So any point in this region between 0 and -4 is on the real axis, and it's also on the root locus because it's to the left of a single pole, 1 pole, and that's an odd number. As soon as we cross from essentially just before -4 to just after, then you realize that again, at this point, there are again an odd number because we have 1, 2, 3 poles that, that this point is to the left of. And so that means that actually all of these points, all points to the left of -4, are also on the root locus because it's also, again, left of an odd number of poles. So notice that the role of complex conjugates essentially doesn't change whether there's an odd number, because essentially you have an odd number here and you're adding an even number 2 to that, which means that it remains odd. The third rule tells us more about the rest of the branches that we don't know information about. So we said that all of the branches start at the poles of L of S, and that m of them terminate, essentially asymptotically terminate at the zeros of L of S. So we said that n is bigger than m, and so if m go to zeros, to the zeros of L of S, then there are n minus m left over, and these go to the asymptotes. I'm missing a y there. And so what we say here is that the n minus m branches converge to n minus m asymptotes, and this rule provides the location and the angles of those asymptotes. So they're centered around a value s is equal to alpha, and we compute alpha. This is a point. It's going to be on the real axis, and it's the sum of all of the pole values minus the sum of all of the zero values divided by the quantity n minus m. And this creates the location where all of these asymptotes originate. So somewhere on the real axis, there's a point alpha, and a certain number of asymptotes originate out of this, and then the angles of these asymptotes are provided by this equation for phi L. And so this says that it's essentially 180 degrees plus this different factors, essentially different number of 360s divided by n minus m. And again, they're going to be n minus m of these asymptotes. And so this, we're not going to go through the full derivation of this, but you can imagine that if you have a pole zero map and you have some number of poles and zeros, that again, this is based on this 180 degree criteria. And what happens is if you take a point a test point all the way out here as k goes off to infinity, then the angles from this point to all of the poles and zeros, this ends up being, as this gets further and further away, all of these angles look about the same. And so this is why we get such a neat formula that comes out of here. And that's the basic idea for where this rule comes from. So we see this implemented on our example. We know that there are no zeros and there are 3 poles. So n minus m in this case is just 3 because it's 3 minus 0. So we know we have 3 asymptotes, and we can calculate the angles and their location. The location is given by the sum of all the zeros and the sum of all the poles. So we take the sum of all the poles, which is 0, minus 4 plus 4i, plus minus 4 minus 4i, and we subtract away the sum of all the zeros. And the sum of all the zeros is just 0. And notice importantly that the complex conjugates of these complex poles or zeros, the imaginary parts are necessarily going to cancel. And so that's why alpha is always going to be on the real axis. And so what's left is this minus 4 and this minus 4, and we get minus 8 over 3. And so the location of where these asymptotes originate is at this minus 8/3. And so from there, 3, because n minus m is 3 asymptotes originate, and they're calculated by this formula, where now we just divide this 180 plus 360 times L minus 1 by 3, because 3 is equal to n minus m. And so if you calculate that for 1, then that's 60, 180. So 60 is equal to 180 plus divided by 3, which is 60, plus 360 divided by 3 times 1 minus 1, because L in this case is 1. And so that gives us the value of 60. Plugging in L is equal to 2 gives us 180, and plugging in L is equal to 3 gives us 300. And so this provides the angles 60, 180, and 300 that describe the angles of these asymptotes. And so now we know the final behavior of these 3 branches. So we know something is going to originate out of this pole, something is going to originate out of this pole, and something comes out of this pole. And based on rule 2, we know that there is a branch that is located on the real axis. And so that makes sense that this one is going to be that branch. And so this branch just extends directly to the left. And now the rest of our task is to understand what happens to these 2 poles, the branches from these 2 poles. Right now, what we can say is that these asymptotes extend further out, and that somehow this leaves, and this branch eventually goes towards this asymptote. And this branch eventually goes towards this asymptote. What we don't know yet is whether that looks like this, or maybe it could spiral around and come up. So that's what we're going to tackle next. Before we do that, there's a nice rule. So we're going a little bit out of order. This is rule 5 now. And this says that when the root locus comes together, and so it indicates a root that has multiplicity, some amount of multiplicity, and so that could be multiplicity 2, 3, or higher, that when the branches essentially come together and then they need to split out again, and the multiplicity, so how many branches are coming together, is q, that the angles that describe them coming together and coming apart are given by this. And so this should look familiar. We've seen this exact formula before, but now instead of n minus m in the denominator, we have this quantity q, which is the multiplicity. And so they come together and they depart at the same angles, and that's given by this theta. And so there's going to be essentially 2q, because there's going to be q coming in branches and q coming out branches. And so let's look at a different example, because our other example doesn't include this. This 1 over s times s plus 1. This we saw this actually earlier in the previous video. We saw how this originally has a pole at 0 and a pole at -1, and that these approach each other and then split at a multiplicity of 2. And so it goes in each direction. And so what we'd like to know is actually what are these angles here? And so the angles are computed just by this formula. And so in this case, we have multiplicity 2, so q is equal to 2. And so that means that we're going to have theta is going to be some multiples of essentially 180 over 2, and that's going to be 90. And so that's why these angles are 90, and then 180, and then 270, and 360. Probably the most complicated formula or rule that we're going to deal with for the root locus, and it's our last one now, going back to rule 4, are the angles of departure and angles of arrival. And so the first thing that we're going to do is deal with the case where we have unrepeated poles. So this is a pole all by itself. And so we want to know what direction, if this is our pole, what direction is this coming out from? Is it coming out at this angle, which we would measure again from the horizontal here? Is it this angle? Or does it come out from this angle, which would be a different angle? And so we're trying to get a sense for what that angle is. And so this again goes back to the 180-degree criterion. So remember that the way we describe the 180-degree criterion is that 180 essentially plus some multiple of 360, where L could be some number. So 180 essentially has to be equal to the sum of all of the 0 angles to our test point minus the sum of all of the angles from the poles to our test point. So this is, say, I, J, J. So if we have a test point S naught, then this represents the angle from the 0 pointing towards this S naught. And this phi represents the angle from one of the poles pointing towards the test point S naught. And so where we get this formula comes from the idea that if we have a pole and we're trying to test what angle it departs at, that we're going to be testing a point that is very close to one of the poles. So this right here is pole J. And so in this case, you're going to have other poles and possibly other zeros that are then going to point towards S naught. And since S naught, we're going to make this very close to this pole that we're trying to figure out the angle from, we might as well just measure the angle directly to this pole, because this S0 is going to be infinitesimally far away from this pole. And so we might as well just measure these angles from the other poles to the pole that we're kind of trying to figure out the angle for, and then from the zeros to that pole again. And so the remainder, essentially, the remainder is going to be given by the departure angle of this pole because that's going to be the angle that this pole, pole J, points towards S0. So that angle is going to be the leftover angle. This gets modified just a little bit when we have repeated poles and we're trying to find the angle. And this really comes back to the idea of Rule 5, which is why I presented it earlier, which is about the multiplicity. So multiplicity said that if the branches are ever coming together, that they need to split away at certain angles. And so you see that that quantity, essentially the previous rule said 180 plus 360 times L minus 1 over Q, where Q is the multiplicity. That term is kind of embedded here in this new formula right here. These two terms together produce that. And so it just means that the departure angles, if there are more than one branches coming out of that pole because it has multiplicity greater than 1, that is just going to be the same formula as what we had above, but now it's going to be divided by this multiplicity that we actually get from Rule 5. Notice that you can go ahead and use this formula even when Q is equal to 1, and you get the exact same answer. So Rule 5 Rule 4 is also useful when we're talking about zeros, and because poles are where the root locus emerges from, so that's departure angles are interesting for poles, but arrival angles are interesting for zeros, because zeros are where some of the branches go as k goes off to infinity. So the branches actually arrive to the zeros. And so a very similar expression is found for the angles of arrival to the zeros. Again, here we're giving it in the generic form with the multiplicity. And the big difference is a minus sign. And that's simply just the role that zeros play instead of poles. And so you can see that we just flipped the order of phi and psi, and that these are pluses now. So to implement this on our problem that we've seen before, so again, we've already seen that we have these three poles at 0 and minus 4 plus or minus 4i. And so the question is, we already know these are the asymptotes, and so we know that in the end, the two branches follow these asymptotes. And we also know from Rule 2 that, and also the asymptote rule, that this is actually going to go out along the real axis. So this pole, we already kind of know what it's going to do. But now the question is, what about pole 2 and pole 3? And so I'm numbering them so we can kind of refer to them. So if we're interested in the departure angle of the pole at the origin, again, we don't really need to calculate this, but it can be just kind of show you how this rule works. The departure angle for pole 1, which is the pole at 0, is equal to the sum of the negative of the sum of all the other poles pointing towards pole 1. So the angle that pole 2 needs to look at pole 1 is this minus 45 degrees. And the angle that pole 3 needs to use in order to look at pole 1 is plus 45 degrees. And so these end up actually canceling out, and so we're just left with the minus 180 term, which gives us again the same information that this pole goes out along the real axis, and that is one of our branches. So now we can take a look at pole 2. And so here, what's interesting is to, again, identify the angles that the other poles would need to use to look at pole 2. And so pole 1, to look at pole 2, needs this angle of 135. And so these angles are always measured from the horizontal. So you measure from the horizontal of pole 1, and it needs to turn and look at 135 degrees in order to look at pole 2. And so that's why we have 135 here. Pole 3 needs to look at 90 degrees here in order for it to look directly up at its complex conjugate pair. And so then simplifying this, that's where this 90 comes from, and then simplifying this gives us minus 405, but if you then modulo that with 360, this reduces just to minus 45. And so this means that this orange branch is going to depart from that pole 2, at an angle of minus 45, which is why we draw it initially descending at 45 degrees, and then it's going to pick up and then eventually asymptotically go towards the asymptotes. Similar argument can be done in order to compute the departure angle of pole at the complex conjugate pole 3, and you'll see that that actually departs at 45 degrees. And so it emerges at 45 degrees, again from its horizontal, and then gradually goes towards its asymptote. And so using all of these sketching rules, we were able to come up with the sketch of this root locus. Once you kind of internalize these rules, it actually becomes quite quick. And finally, just to summarize these are the different steps that you should use as you're going to approach a root locus. So based on the loop transfer function that you're given, with m zeros and n poles, that the root locus start, the n branches of the root locus start at the poles of L of s, the roots of that denominator, and that m of these converge to the zeros of L of s. And m is always going to be less than n. And so the remaining of those branches are then going to converge to asymptotes. And we can compute those asymptotes radiating out of a point alpha, which is going to be on the real axis and at angles phi L. A really handy tool that helps you make your root locus diagrams quite quickly is the fact that the root locus is always going to be on the real axis to the left of an odd number of poles and zeros. And so that really helps nail down where certain branches go. And then you use the angles of departure and arrival in order to calculate the fine grain information about poles and zeros. Oftentimes, some of this can already be determined from the asymptotes and the real axis rules. And that's just because you can automatically know that it's going to leave at minus 180. And then finally, if there's multiplicity where different root locus branches meet and then have to depart, then we use rule 5 in order to determine that. So just when you see a problem, just go 1, 2, 3, 4, 5 through these rules, and that should give you a lot of information, generally enough information to put together your root locus sketch.